So in part A, we just need to sketch the locus of z that satisfy this condition here. So let's think about it algebraically to start with, geometrically, sorry. So to think about it geometrically, we need to write it as z minus some complex number. So inside the bracket, I'm going to put minus 3 and minus 2i. So that when I multiply out the bracket, I get plus 3 and plus 2i. So we've done quite a few of these now. We know that this is going to be a half line, which starts at the complex number minus 3 minus 2i. So let's sketch minus 3 minus 2i. So I'm going to label minus 3 minus 2i as a green dot. And we know that it's going to be a half line which comes off at an angle of 3 pi over 4. So 3 pi over 4 is going to be like that. And it makes that angle with the positive horizontal. So I'm going to label that as 3 pi over 4. So for part B, we need to come up with what the Cartesian equation of the locus is. So we'll look at two different ways. We'll do the better method first, which is kind of like using the formula. So we're going to say, well, let's say z is some complex number x plus iy. So z has coordinates x plus iy. Then we can substitute this into the locus, the equation of the locus. So we've got the argument of replace z with x plus iy, plus 3 and plus 2i has to be equal to 3 pi over 4. So just like we always do, now when we do it algebraically, we're going to collect together the real part of this complex number inside the bracket. So the real part is x plus 3, and the imaginary part is y plus 2. So we've got y plus 2, and take I outside the bracket. So we're now just going to use the formula that if we do, so we've got this complex number here inside the bracket in yellow, and we know that the argument of this complex number is 3 pi over 4. Well, we're going to use the fact that if we do tan of a complex number's argument, so tan of 3 pi over 4, that is always equal to the imaginary part of the complex number. Well, the imaginary part of this complex number is y plus 2 divided by the real part of this complex number, which is x plus 3. Well, tan of 3 pi over 4 is minus 1. So we know that minus 1 is equal to y plus 2 over x plus 3. And we can rearrange that to get y plus 2 equals minus x minus 3, or y equals minus x minus 5. And really, I should have the condition here. We need to show that it's a half line. This is only valid for x values, which are to the left of minus 3, because we don't want the line to continue down here like that. Okay, so we need to put x is less than minus 3 for x less than minus 3. I guess an alternative way of doing that would be to say, well, let's do a bit of trigonometry on this line to work out what the gradient of this line is. Well, let's draw in a right angle triangle like that. And let's label this side length as opposite and this side length as the adjacent. And what we want to do is we want to work out the gradient of this line to work out the equation. In this right angle triangle, that angle there is going to be pi over 4. So first of all, we can say that tan of pi over 4 is going to be the opposite side length divided by the adjacent side length. Well, tan of pi over 4 is just equal to 1. So opposite divided by the adjacent in that right angle triangle is 1. Well, the gradient of this line, we've got to be a little bit careful here. Remember, opposite and adjacent are both positive, they're side lengths. The gradient of this line, the change in y is going to be minus the opposite side length because it's going down, and divided by the adjacent. So the gradient is actually going to be equal to minus opposite divided by adjacent, so minus 1. Okay, and then we can just use the fact that it goes through this point with coordinate minus 3, minus 2, and we'd get the same answer that we got before. So if we were to use this method, we'd have y minus 2 equals the gradient x minus 3. And we'd get the same answer that we got before. Okay, in part C, we need to find out what complex number satisfies this locus that we just, this condition that we just sketched, and also this condition here. So we know that it has to lie on this line here because it satisfies that condition there, but it also has to lie on this locus here. So let's think about what this locus of points is. Let's just think about it geometrically. Remember, if we were to think about this geometrically, we're going to write that as z minus, and then inside the bracket we're going to have to put minus 3 minus 2i is equal to 10. So remember, we think about z minus 3 minus 2i as the vector that goes from minus 3 minus 2i to z. And we've got modulus symbols around it, so we want the length of that vector to be equal to 10. So this is going to be all the points that are a distance of 10 away from this point here. So all the points that are a distance of 10 away from there, that's going to be a circle, radius 10, because we want it to be a distance of 10 away, and centre minus 3 minus 2i. So I'm not going to draw it very accurately, but if we were to sketch on that circle, it's got the centre of the circle is this green point here, and it would be some circle, I'm not drawing it accurately, with radius 10. And we would want what is the coordinate, or what is the complex number there at the, which is both on this locus and on that circle. Well, we can obviously just write down what the equation of this circle is because we know the centre and the radius. Let's practice finding the equation of the circle algebraically. So let's take this locus here and let's use an algebraic method to find the equation of the circle. So we're going to say z is equal to x plus iy, and we're going to replace z with x plus iy. So we're going to have x plus iy plus 3 plus 2i, and the modulus of that complex number is equal to 10. So remember to solve this, we're going to collect together the real part. So the real part is x plus 3, and the imaginary part is y plus 2. Take I outside the bracket. And the modulus of a complex number is equal to the square root of the real part squared plus the imaginary part squared. That's a formula that we really need to learn. That the modulus of any complex number is the square root of the real part squared plus the imaginary part squared. So we've just applied that concept to this yellow complex number inside the modulus symbol there. So we can expand that out, and we're going to have x plus 3 all squared plus y plus 2 all squared, square both sides, equals 100. And that is the equation of the circle, just as you would expect the equation of the circle to be that we just drew there. So our last step is to find out what coordinate xy satisfies both this condition, the equation of the circle, and also this condition, the equation of the line. So let's solve these simultaneously then. I'm going to replace y with minus x minus 5. So we're going to have x plus 3 all squared plus minus x minus 5 plus 2 all squared equals 100. So we're going to have x squared plus 6x plus 9. And then this bracket here we can simplify to minus x minus 3 all squared equals 100. So if we multiply this out, we're going to have x squared plus 6x plus 9 plus x squared plus 6x plus 9 equals 100. So we've got a quadratic which we can solve. We're going to have 2x squared plus 12x minus 82 equals, and if we solve that, we're going to have two solutions for x, either x equals minus 3 plus 5 root 2, or we'll have x equals minus 3 minus 5 root 2. Well, let's go back to our drawing and check what we're actually looking at. So we know that it has to be on this line and also on this circle. Well, we're getting two solutions because the equation of the line is actually an equation that includes this point of intersection here. Well, we know that x has to be less than minus 3, so we want only this coordinate here, because this is not part of the line. We don't want that part. So we want this solution here, because, and we can say that, not a solution, because we know we want x less than minus 3. And then finally we use the equation y equals minus x minus 5 to find out what y is. So y equals minus 2 plus 5 root 2. So remember, we were asked in the question for what complex number z satisfies this. We're not quite done, because we know that z, the complex number, is x plus iy. We've just found the coordinates of the complex number. We've not actually written it as a complex number. So our last step is just to say, well, z is actually going to be equal to x plus I multiplied by the y value, which is minus 2 plus 5 root 2. So I've shown you the general approach for solving a problem like this, because in the exercise there's lots of problems with the intersections of lines and circles. In this specific example, you could have solved it a little bit easier actually, and the way that you could have solved it, because we know that the line goes through this point and that's also the centre of the circle, you could have used the fact that you know that this length here, because this is the centre of the circle, is just the radius of the circle, which is 10. And if you're drawing a right angle triangle like this, then because that angle there is pi over 4, you know that this is actually an isosceles triangle. So this would also be pi over 4. So these two side lengths would have to be the same as each other, these two red side lengths. Okay. So you could have said that this, let's say that side length is A and that side length is A, because we know this is an isosceles triangle, because pi over 4 is 45 degrees. And then you could have just used Pythagoras actually to work out what A is in this case. So in this case, we know that A squared plus A squared equals 10. So A squared, 2A squared equals 10, and A is equal to root 5. So to find the coordinate at this point, we could have just used the fact that we've moved from this point minus 3 minus 2 left by root 5, so the x coordinate would be minus 3 minus root 5, and we've moved up by a, so the y coordinate would be minus 2 plus a, which is plus root 5. Okay, but this is just very specific to this example, which is why I showed you the general method, which would be to solve the simultaneous equations. It's probably the preferred method.